So in today's video, what we're going to do is we're going to try and move past right-angle trigonometry. So we're going to extend these trig functions from right triangles out to just the general coordinate plane. You'll remember at the very beginning when we were looking at angles, we put them in standard position on a set of axes. And so we're going to go back to that look and we're going to say, okay, how do we switch this idea of right angle trig, that SineCosine, sine is the opposite leg over the hypotenuse, etc., etc. How do we extend that to just the regular coordinate plane? Then we'll look at sines of trig functions in different quadrants, and we'll see how things go there, and we'll talk about reference angles and things like that. So only a couple of things in this video. Main thing is we got to remember, or at least recognize, what the main issue is. The main issue is that when we're looking at right angle trigonometry or right triangle trigonometry, we've got these nice right triangles here. There's our right angle, and we'll say that's some angle theta. If we want to find all of our trig functions here, we said that the domain of our trig functions is relatively small, the possible inputs. So the domain at this point, we said, was anything in between 0 and 90 degrees, or we could say between 0 and pi over 2 in radians. We can't have an angle smaller than 0, because that doesn't make sense for a triangle, a negative angle. We can't have that angle equal 0, or else our triangle just looks like this, a straight line, and that's not very interesting. And we can't have an angle equal to 90 degrees, because then our triangle will look like this, and these two sides will be parallel. We don't actually have a triangle anymore. This is not a closed figure. So the domain of our trig functions is relatively limited here, because we're only able to have these few angles in a mix if we're stuck on looking at a right triangle. So we want to push past right triangles so that we can look at any angle. So something maybe with a negative angle, or something bigger than 90 degrees, or pi over 2. So that's the main issue. That's what we're going to try and fix. So we know that an angle has an initial side and a terminal side. What we've been looking at is something like this. So here's our angle. Let me throw our little arrowheads on here. And if our terminal side ends up in the first quadrant like this, then we really have our regular old right angle. Maybe I'll change colors for that. We really have our regular old right angle trigonometry. We could drop a line down here, and there's our normal right triangle. This picture looks a lot like this one. It's just kind of flipped around, but it's the same idea. That angle is somewhere in between 0 and 90 degrees here. But we can have the terminal side of our angle end up in any quadrant that we'd like. So maybe there's our initial side, and we have a terminal side that looks like this here. And now we don't have a right triangle anymore explicitly for this angle. But what we can do is form a kind of implicit one. I'm going to use red for this one. We can still drop a vertical line down, and we'll notice that this triangle here is a right triangle. Maybe I'll use red again for this side length. There's a right triangle that we have. And this angle that we have here is, maybe I'll do this. It's not theta. Sometimes people will call it alpha. Sometimes people will call it theta prime, or they'll put a little tick mark on it. But it's some other angle. So maybe I'll just write that in here. Some other angle. And really what it is, it's a supplementary angle. You might remember that from your high school trigonometry stuff. What we mean when we say it's supplementary is that if this is some angle like theta prime, we're going to say that that plus theta is equal to 180 degrees, or equal to pi radians. That's an equal sign. There we go. So whatever this angle is, question mark here, plus this green angle, that's just going to add up to 180 degrees. So we can look at some right triangle, and then we could go ahead and do some trig stuff on here. And that's, in general, the way that we're going to do things. So what we're going to do is we're going to define these angles now by points on the coordinate plane that the terminal side passes through. And these points are going to look like x comma y. We're going to say, okay, x comma y, whatever that point is some point on our angle here, or on our terminal side of our angle, sorry. And we can see on our triangle that that's the x value, and that's the y value. And this value here, we're going to call r, the length of that hypotenuse. We're going to call it a radius, where r squared is equal to x squared plus y squared. You'll notice this looks really similar. This is really a squared plus b squared equals c squared. It's just the Pythagorean theorem for a right angle triangle. So if we think about this point, we can use the coordinates to go ahead and talk about the sides of our triangle. That's the exact same thing here. We've got x and y and r here. And if we did some other blue angle, I don't know, let's put it down in like this quadrant. We could say this blue angle seems to pass through, there's my arrowheads, seems to pass through some point here. And if we extend a vertical line, we've got a right triangle. And again, we've got an x value here. Oof, that's a bad x. We've got an x value here, a y value here, and a radius here. So if we want to talk about angles, we'll definitely think about some angle theta. And in this case, here's theta. But we're going to reference these angles by a point that they happen to pass through on the coordinate plane. So we can go ahead and come up with trig functions based on this pretty easily. So here's our general trig function stuff. You'll notice that we have some different kind of notation here. Let me just draw a quick set of axes so I can kind of point out what's going on here. I'm going to put my angle going this way. Maybe actually, I'm going to redo this. I'm going to put my axes in black so I can see my angle a little bit easier. So I'm going to have some sort of an angle with an initial side and a terminal side over here. And we're going to put some point here. We're going to drop some vertical line down here. And we're going to say that point is, that point is x comma y. So this is just filling in the stuff that we had before. And there's r. And so now if we want to find sine of this angle, notice it's not the one in that triangle. We're going to define it as the same kind of thing as if we were just looking at this little right triangle. We're going to say it's the opposite side, y, over the hypotenuse, r. So when we're looking at sine theta, we still have a kind of opposite over hypotenuse setup. For cosine theta, then, we're going to do the same thing. We're going to say it's the adjacent leg, but it's not really of that angle. It's this little inside one. It's the supplementary angle in this case. We're going to say there's an adjacent leg here, x, over our hypotenuse, r. So cosine is still adjacent over hypotenuse. And for tangent, it's going to be opposite over adjacent, so it's y over x. But now, since these values can be anything, x and y, since we can move them around anywhere, we do have to make sure that we don't divide by 0. So there's some new stuff that we have to think about. We didn't have to think about this on a right angle triangle, because if we were forced to be thinking about just a triangle, we're never going to have one of the side lengths be 0. But if we're thinking about points in the coordinate plane, we could have a point where an x value is 0. It could be right on this y-axis. We could put a point right here, and then we'll say, in that case, tangent is undefined because we divide by the x value of 0. That's a little bit weird, but something to keep an eye on. Notice we still have this same behavior where cosecant is just the reciprocal of sine, right? We flip that thing upside down. Secant is still the reciprocal of cosine, and cotangent is still the reciprocal of tangent. Notice on all of these, we have some domain restrictions because we're dividing by values that could be 0. For sine and cosine, r is never actually going to be 0 until x and y are both 0. But that means when we're thinking about this distance, we'd have like a 0 distance if our point was actually on the origin. But that really doesn't define an angle because we'd be looking at a line that goes, I know this is really bad, but oh well. We'd be looking at a line that goes from this point to this point. So that's our picture of an angle where x and y are both 0, meaning r would be 0. Meaning that's kind of like it's a vacuous case, we could think of it, where there's nothing that exists there. There's no angle here anyways. And so it doesn't really make sense to define a trig function on a non-angle. Anyways, if theta is some angle in standard position and we have this real radius here, then we can think about just the point on the terminal side and get all of our trig functions defined in the same normal way. The key here is to be able to drop a vertical line to get that nice right triangle. So how do we know exactly how to do all that stuff? Well, we're going to build up to that. But first, what we're going to notice is that since we're able to move into different quadrants, we can get different signs of our trig functions. Now, I'm going to just look at sine and cosine for now, and then we'll think about all of our other trig functions. So I'm going to put my initial side right here. We're going to put our angle in standard position just like normal, but then I'm going to draw 4 different terminal sides. So I'm going to draw a terminal side in the first quadrant. So here's my angle. And then I'm going to draw one in the second quadrant, and then the third quadrant, and then the fourth quadrant. And we're just going to think about what happens to sine and cosine. I'm going to do sine in red, and I'm going to do cosine in blue. Let's think about really x and y values. I'm just going to state something right off the bat. R is always positive. Or if you want, you could say r is greater than 0. I like to use just a little plus and minus sign for positive and negative like this. Actually, that's going to be confusing because theta kind of looks like minus sign. So I'm going to get rid of this, and I'm just going to say r is greater than 0. So what that means is that when we think about sine of theta and how that's y over r, and cosine of theta and how that's x over r, in the way that we defined that in the previous slides here. Sine is y over r, cosine is x over r because of this little picture here. If we define it like that, then what we're going to do, I'll say sine is red and cosine is blue. Oops, that's green. I promise I'm not actually colorblind. I do know the difference. So if we look at this point, we'll say this point has a positive x value. So that means our cosine function has a positive x over a positive r. So in this quadrant, cosine theta is greater than 0. It's positive. Similarly, we have a positive y value here, meaning sine has positive over a positive. So that means sine of theta is greater than 0. Now that's going to change when we switch to a terminal side somewhere over in this quadrant, because now if we pick some point that we pass through, x comma y, our y value is still positive. We're above the x-axis, but now since we're on the left side of our Cartesian plane, the x value is negative. So since the y value is positive, we'll say sine of theta in this quadrant is still greater than 0. But since our x value is negative, our cosine function is going to spit out some negative number over a positive radius, meaning cosine theta is actually going to end up being a negative number. Then we can go ahead and say, well, what if we put an angle in the third quadrant? Oh, let me actually put that from the origin. There we go. If we do something like this, then when we pick some point here, we'll call our point x comma y. And I'm drawing my y's really weird today. I don't know why. Let me fix that. That's what a y looks like. Then what we'll notice is now both the x value and the y value are negative. So our cosine function is still going to be negative. But also, since we're underneath the x-axis, since our y value is negative, our sine value is going to be negative. And then lastly, we'll pick a fourth angle. We'll put that somewhere here. And we'll say if we pick some sort of a point on here, x, comma, y, then our x value is positive. So cosine is positive, and our y value is negative. So sine is negative. So I want you to take a look at something here. We have these signs for cosine and sine. It's tricky to think about signs, but when I say signs first, I mean positive, negative. We have the positive, negative signs of a sine function and a cosine function. And we can see some patterns. Since the sine function depends on y, then when our point is on this side of our axis, when the y value is positive, notice that sine is positive. When our y value is down here, when our point is underneath the x-axis, we get a negative y value. So notice we get negative sines. For cosine, it's dependent on x, and so we look at horizontally where our point is. If we're over here somewhere, if we're on the right side, we have a positive x value. Cosine is positive, and cosine is positive. And over here, on the left side, we have a negative x value, so cosine is negative for both of those quadrants. So this only is telling us about these two functions, sine and cosine. We can obviously get secant and cosecant by just looking at the cosine and sine function, right? Since secant is just the reciprocal of cosine, it's the opposite thing. It's going to have the same positive or negative sign because it's just going to be r over x. It's still dependent on the same x value. Same thing for cosecant. Cosecant is just r over y. It's the reciprocal of the sine function, and so it's going to have the exact same positive or negative sign. The only one that we really need to think about is tangent. So let me go ahead and think about tangent theta in both of these. Tangent we can think of as sine over cosine. And so what we'd like to do, maybe I'll just do it like this underneath. Since tangent theta, oof, my thetas are bad today too. There we go. Since tangent theta is really sine of theta over cosine of theta, we can say it's going to be a positive number over a positive number, meaning in this quadrant, tangent of theta is greater than 0. Over in this quadrant, tangent of theta is a positive number over a negative number, meaning tangent of theta is negative all around. In this one, we have that tangent of theta is a negative number over a negative number, meaning tangent of theta is negative. Oops, that's not true. What am I thinking? Tangent of theta is positive. Negative over negative is positive. And lastly, we have tangent of theta, in this case, is a negative over a positive, and so that means that tangent of theta is negative. So for the tangent function, you'll notice that since it depends on the signs of positive, negative sign of both the sine and cosine function, when the sine and cosine function act the same, tangent is positive. So in this quadrant and in this quadrant, sine and cosine are both positive or they're both negative. And that means we get a positive tangent. And that means also we get a positive cotangent. And in this quadrant and this quadrant, sine and cosine are opposite signs of each other. One of them is positive and one of them is negative. It doesn't matter which one is which. As long as they're different, we're going to get a negative tangent function and then also a negative cotangent function. So these are the things that we should be thinking about here. We should be able to recognize, based on the quadrant that we're in, what kind of answer we're getting out of our sine, cosine, and tangent functions. Really, we only need to know sine and cosine because you can get tangent from there. And then once you know sine, cosine, tangent, you can get the signs, positive or negative, for cosecant, secant, and cotangent because, again, they're just reciprocals. So they're going to follow the same sign, positive, negative, as the sine, cosine, tangent functions. Cool? Cool. Reference angles. Let's say theta is a non-acute angle in standard position. Non-acute technically doesn't mean obtuse. It means it could be obtuse or 90 degrees. It could be a right angle. But it's not less than 90. So let's go ahead and draw one. Let's put it, I don't know, we haven't done one in the fourth quadrant very much. So let's say this is our angle. I forgot to draw my little arrows on here. And our angle is this. All the way around. So it's a pretty big angle in this case. So we're going to talk about a reference angle, and it's going to be a positive acute angle formed by the terminal side and the x-axis. What does that mean? Well, this is exactly what we were doing earlier. What we're going to do is grab our terminal side and draw a vertical line to connect the x-axis. And we're going to say this is the reference angle, which we're going to call theta prime. Some textbooks will just use a different Greek letter altogether, and they'll say things like it's alpha or beta or gamma or something like that. This textbook that we're using uses theta prime, so I'll try and keep that notation consistent throughout here. It's going to be a different kind of thing. In this case, you can notice that it's really not a supplementary angle anymore, like it was in our other example. It's an angle where it adds all the way up to 360. It's not going to be the negative version, so we're actually going to be traveling in this direction here. So it's not in standard position, really, because our initial side now is actually the old terminal side, and our terminal side is the old initial side, which is a little bit weird. That's not even always the case. If we put something in the third quadrant, then we can draw a reference angle, and it's going to be completely different. If we do something like this, and we say theta is this angle, then when we grab our terminal side and we draw a vertical line to connect our x-axis, then theta prime, oops, I want not a straight line, there we go. Theta prime is actually this angle here. So it's a little bit tricky to exactly see what's going on with this. Sometimes people will want to draw horizontal lines and connect. Oh, I should draw a straight line. Sometimes people will want to do a horizontal line, and they'll say that like this angle in here is something. But that's not going to be what we look at. So maybe I'll just put a big X there. Don't do that. We're only going to be drawing vertical lines to connect to the x-axis here. Mostly, that's just something that we've kind of standardized for some specific reasons. And if you want to get into that more, you can shoot me a message or put it up in the discussion boards, and I can get into that a little bit. But really, we're going to get used to just connecting the terminal side and the x-axis here. That's going to be the main thing. So here's some examples. We're not going to actually do anything with these. What we're going to do is draw the angle, and we're going to see if we can figure out what the reference angle is. So I've got two examples, degrees and radians. I'll do 1 degree, 1 radian, and then I'll let you do the other degree and the other radian, and we'll see how things go. So let's draw 345 degrees. Sometimes these are hard to draw. So I think in the way that you think about where these angles are, it kind of leads us to thinking a little bit about reference angles anyways. Let me show you what I mean. I'm going to draw my initial side. Oops, I want a straight line. Here we go. There's my initial side. I know that 345 degrees is going to be in the fourth quadrant. How do I know that? Well, because our quadrants are set up by 90 degrees, right? So 0 to 90, anywhere in here is our first quadrant. 90 to 180 is our second quadrant. 180 to 270 is our third quadrant. And 270 to 360 is our fourth quadrant. So I know this thing, oops, is in the fourth quadrant. Maybe I'll just do this. You've probably seen this before, quadrant 4. How do I know exactly where it is? Well, I know it's pretty close to 360, so I know it's going to be really close to like a full circle. How close is it? Well, it seems like it's 15 degrees away, right? 345 plus 15 is 360. And so let's say that that's a pretty good thing. And this is 345 degrees. So where's my reference angle here? This is theta. My reference angle is going to be this one, right in here. So what we're going to do is say theta prime is going to be the difference between 345 degrees and 360 degrees. It's a positive angle, so we just want to make sure that that difference is positive. So I'll say 360 degrees minus 345 degrees. That's 15 degrees. So remember when I said, okay, 345 degrees is going to be really close to this because it's about 15 degrees away? Well, that's me finding the reference angle. It's helping me understand where it is. Now, I could have graphed 345 degrees by saying, well, I know this line here is 270. This one here. And so I could say, all right, it's 270, and then I have to go another 75 degrees to get this. So I could say, all right, this here is 75 degrees. That's not a reference angle, because that would be the angle between the y-axis and our terminal side. And we want to find the angle between the x-axis and the terminal side. So I'll consistently think about that kind of thing. Let's do this in radians then. So in radians, it's going to be the same kind of thing when we graph these, except instead of thinking about 0 to 90 degrees and 90 degrees to 180 degrees, we'll be thinking about angles between 0 and pi over 2, and from pi over 2 to pi, and from pi to 3 pi over 2, or 1.5 pi, and from 3 pi over 2 to 2 pi, or from 1.5 pi up to 2 pi. So we'll just be moving by half pi's. This, is close. Oh, I know. Keep wanting not a straight line. Say this is close, but less than. I should put 2 up here. It's close to, but less than pi. 6 pi over 6 would be pi. So 5 pi over 6 is a little bit less than pi. So that means it's a little bit less than, let me do this a bit better. There we go. This line here, so it's going to be somewhere in our second quadrant. So this angle here is 5 pi over 6. Our reference angle is going to be, bang, right here. So I want to find this reference angle. That's going to be theta prime. I know it's going to be the angle in between pi and 5 pi over 6. I know it needs to be positive, so I'm going to say this is really pi minus 5 pi over 6. Pi is really 6 pi over 6, so this is just a pi over 6 reference angle. So there's the 2 reference angles here. I've got 2 more examples for you. I've got 94 degrees and 5 pi over 4. See if you can find some reference angles for those. I will let you pause the video, and then when you come back, I'll have some stuff drawn up and some work written out, so hopefully you'll be able to see exactly what's going on there. All right, go. Hopefully your pictures and your reference angles look like this. So let me just kind of run through these really quickly so we can kind of explain what's going on. On this first one with the degrees, the 94 degrees one, oops, I lost my pen. There we go. I know that 94 degrees is just a tiny bit bigger than 90 degrees, right? It's 4 degrees more. And so sometimes it's really easy for people to say, oh, my reference angle is 4 degrees. But that would be an angle in between your y-axis and the terminal side. And so remember, we want to drop down to the x-axis, so it's actually going to be the angle that we need to bounce this thing up to 180 degrees. So it's going to be 86 degrees here. So hopefully you got that. 5 pi over 4, people struggle sometimes with radians, so let's talk through this. I know that if I divide this thing up into pi over 4s, pi over 4 is here, pi over 4 is here, 2 pi over 4 is here, 3 pi over 4 is here, 4 pi over 4 is here, that's pi. So 5 pi over 4 is going to be right here in the third quadrant. Or you can say 5 pi over 4 is bigger than pi, and it's bigger than pi by pi over 4, which is halfway in between pi and 3 pi over 2, 5 pi over 4s. So we know it's going to be right here, splitting this thing equally. Our reference angle then is going to be the angle in between 5 pi over 4 and pi. So subtract them, we get pi over 4. Every now and then, people will mix up the order of these. And they'll say things like, oh, my reference angle is pi minus 5 pi over 4, so it's negative pi over 4. Remember that in our definition of a reference angle, it's going to be a positive acute angle. So if you switch up the order and you get a negative reference angle, no big deal. Just think about that as like use the absolute value, I guess. Just make sure you look at the positive version of this. And so that's how we can find reference angles of this thing. We can evaluate trig functions using reference angles. That's the main thing that we're building up to. And we know we have, these definitions where we have like x and y and all that stuff, but we also have some known angles or known triangles that we can use to do all this stuff. And so that's what we're going to do here. We're going to look at two angles. We're going to evaluate them by using some reference angles. Okay, first things first. Graph these. Sketch these angles. You can put the 5 pi over 6 over here. Whoops. So let's say theta is 5 pi over 6 can go here. 5 pi over 4 can go here. See what you got. Did you do it yet? If not, pause the video and actually do it. Let me get rid of these. All right, so hopefully you've got these things sketched. If you really need to, if you haven't yet, one of the things that you can do, I don't love it, but you can do it, is just convert these things to degrees. My guess is that you all have a bit more intuition with looking at angles in terms of degrees. And so you can go back to that very first thing, that very first video when we talked about how to connect degrees and radians and just switch these things over. I don't like doing that because for the rest of your math career, I guess, you'll likely be using radians most of the time, especially when you get to calculus. This class is a preparation for calculus, and so most of what you'll see there is going to be using radians. And so I like to keep as much as I can in radians and just get used to it as soon as we can. Anyways, I'm kind of stalling so that if you haven't done this yet, you still can. But let's go ahead and do this thing. 5 pi over 6 we've already drawn. Looks like this. Our reference angle, we know, is right in here. Oops. And that's theta prime, and we know that that's going to be pi over 6. What I want to do is I want to draw this triangle right here. You could think of it as kind of like a reference triangle. I'm just going to draw this down here. Make it a little bit bigger. I'll go up to there and I'll connect that. There we go. And we know that this angle right in here is pi over 6. Or if you want to think about this in degrees, you can convert that. And what's that going to be? Well, that's 30 degrees. So if this is pi over 6 or 30 degrees, that means that up here is 60 degrees or pi over 3. And hopefully you recognize this 30, 60, 90 triangle. This was one of those triangles that we said we should just know. We said that this distance here was 1. This distance here was twice that. I guess we could scale these, right? If we say this is 3. I don't know why I drew my 1 so weirdly. That's 1. That's 2. And then this one here was going to be root 3, right? Now, when we do the Pythagorean theorem, we get 1 squared plus root 3 squared. That's really 1 plus 3, so that's 4. And this here is root 4. So there we go. So let me draw this on here. 1, root 3, 2. Now when we draw it on here, our coordinates for this point are not actually these values, but they're close. Our x value is going to be root 3, but be careful, we're in the second quadrant. This is actually negative root 3. So we have negative root 3, 1. And now what we can do is we can say, well, let's figure out what sine and cosine and all that kind of stuff are. So we could say, maybe I'll write this under here, sine of 5 pi over 6 is equal to, you could either say it's the y value over r here, or you could say it's just the opposite over the hypotenuse, just the same way that we always have done. So it's half. cosine of 5 pi over 6 is the adjacent leg over the hypotenuse, or it's x over r. So this is negative root 3 over 2. And we could go ahead and figure out what tangent is and what cotangent is and secant and cosecant and all that stuff. Really, we don't even have to have this picture anymore, because once we have the value for sine and cosine, remember, we can use identities to get the rest of them. So if we just draw this little triangle off to the side, we can get the values here, and then we can get the coordinates, and then suddenly we've got values for sine and cosine. Let's do the same thing with 5 pi over 4. We've already drawn this, so I'm not going to play anymore. 5 pi over 4 is right here. We already know what the reference angle is. I need my initial side as well. There we go. So we're going all the way around there, but our reference angle is going to use this triangle here, and we know that this is pi over 4. So we'll say theta prime for our reference angle is pi over 4. Okay, so what we can do now is just draw this triangle off to the side. And again, we're going to notice that this happens to be one of our special triangles. I drew it too big, so let me get rid of this. There we go. And if this angle, oops, in here is pi over 4, then so is this one. Because everything needs to add up to pi. This is pi over 2. Or if you want to convert it to degrees, this is your 45 degree isosceles right triangle. So if this is an isosceles triangle, we know that these two side lengths are the same. Let's call them 1. It doesn't really matter what they are. And then this is going to be root 2. It's the square root of 1 squared plus 1 squared using the Pythagorean theorem. So let's go ahead and put those in. 1, root 2. But really, this is a negative x value and a negative y value, because we're thinking about this point right here. That point is negative 1, negative 1. So all we have to do is just be a little careful about signs. Positive, negative, and we've got everything. Over here we can say then that sine of pi over 4, 5 pi over 4, there we go, is going to be the opposite over the hypotenuse, negative 1 over root 2. Or if you want to rationalize this, you can get negative root 2 over 2. I'm okay with either. Cosine of 5 pi over 4 is going to be the same thing. Notice third quadrant, so both of these are negative. So you'll notice that tangent of 5 pi over 4 is going to be positive 1. It's negative 1 over negative 1. So just like we said, third quadrant, tangent's going to be positive. In these opposite ones, it's going to be. So you can do all that kind of stuff just using these reference angles. So that's the main idea that we're looking at here. This is a relatively long video, so sorry about that. I'll try and keep them a little bit shorter. Go back through everything if you need to. There's a lot going on here. Good luck.